Okay, hello everyone. Welcome to the 19th IEEE International Multi-Conference in System Signals and Devices 2020. And today we are specifically presenting one of the keynote for the International Conference on Power System and Smart Energies. And my name is Francisco Gonzalez. I am a full professor in electrical power systems at the University of Southeastern Norway and also the leader and founder of the DHENSYS Lab, Digital Energy System Laboratory. And today the topic is quite interesting. Today I will tell you about low in rotational inertia systems and grid-friendly power electronic converters. And before I start, I would like to tell you that, as usual, all the slides will be available at my ResearchGate repository. And also, if you have the opportunity to visit my YouTube channel, I highly suggest that go over there because also you will find the full video. And let's start with a short agenda. I will start with a short description and discussion about the path to net zero, reaching the important target of zero net carbon emissions. Then I will tell you about the transition, the situation that is happening in the energy sector right now, because reaching the net zero imposes a challenge. And from there, we will discuss what is the issue. What is the issue specifically for electrical power systems? And what is important for you in this class today, in this keynote speaker, is that we will be talking about reduced level of synchronous generation. From there, we will discuss some of the main issues. Reduction on fault levels, specifically short circuit currents, then reduction in reactive power support, and reduction and inertia, rotational inertia. Then we will discuss some methods to enhance the system frequency, the system stability, and we will discuss about two different paths to discuss these solutions. One of them is the short-term solution, and that include the mitigation measures, but also how can we reduce the risk using some situational awareness systems inside the electrical power system. Something like the very well-known inertia monitoring and estimation methods. And then I will discuss some of the long-term method for enhancement the system stability. Specifically, I will talk about these very famous grid-friendly power electronic converter techniques that is known as grid forming. But let's start with this very important transition that we are happening worldwide. As you must be aware, climate change is a reality, and it has been declared as global emergency. As the CO2 emission increase, the global warming is affecting in many different ways the society, and as a consequence, the pressure to stop this global warming and to do something to reduce the accelerated progress of CO2 emission has been extremely important. And there is a reason that many countries around the world, they have been fully committed in terms of reaching the target of zero emission. There is a website that is called the Net Zero Tracker, and if you go over there, you will see that there is a massive number of countries around the world that they are already committed to reaching the net zero. However, some countries already they reach this value. For instance, the case of Suriname or Bhutan, they already are net zero. In other countries, is already a piece of legislation that you can find that is committed to reach the net zero. That is the case, for instance, that the United Kingdom is committed to 2050 in law to reach the net zero. In other countries like Canada, South Korea, Spain, is a proposed legislation with the year 2050 as the common denominator for reaching the net zero. However, coming back to the case of the United Kingdom, in the United Kingdom, we have in law that for 2050, we need to reach the net zero. However, there are a pressure in many part of the British society to reach the net zero. And there is a reason that individual cities, important cities in the UK, like Manchester, is trying to reach net zero for 2038. Is committed like Bristol for 2030 and the famous city of Glasgow in Scotland for 2030. For more details, go and visit this net zero tracker and you will get an information. However, coming back to the country, to the United Kingdom, it's very important that you understand that the massive part that we need to reduce the CO2 emission is specifically the electricity sector. But to be honest, UK has been committed in the climate changes for many decades. In 2019, the UK Parliament passed a legislation that is called UK Climate Change Act. And in that is already establishing the net zero by 2050. But in the electricity sector, the decarbonization has been extremely fast. And there is the clear target that we are moving to reach net zero carbon emission in the electric sector. However, many people believe that this is something that is unrealistic. But the reality is that in recent time, we have been pushing very hard to reduce the CO2 emission. In 2013, the emission of the electricity sector was around 529 grams or CO2 per kilowatt hour. In 2020, it was 181 grams the CO2 for kilowatts hour. We are talking about more than 65% decrease between 2013 and 2020. But what is extremely important for you to understand is that we already has reached very low values, instantaneous low values of zero carbon. For instance, in 5th of April 2021, we reached the minimum of 39 grams of CO2 per kilowatt hour. With these numbers, what I am trying to tell you is that it's a full reality that the UK is fully committed to the net zero. And the important part is that the electricity sector, and specifically National Grid electricity system operator, is committed to that. But it's not only the United Kingdom. It's also many other countries around the world. There is already a document from the International Energy Agency talking about a roadmap for the global energy sector to reach the net zero for 2050. And if you look this piece of document, they are very important information. And if you look the target for 2030, you can see that 1,020 gigawatts annual of solar and wind power addition will happen by 2030. By 2035, the overall net zero emission electricity, it will be reached in most of the most advanced economies around the world. For 2040, net zero emissions is probably to be reached at global, around the world, net zero emission in the electricity sector. And finally, for 2050, something that is extremely important is that almost 70% of the electricity generation globally will come from solar PV and wind power. For that reason, we are talking about that 2050 will be a very important year, because also the measurements to absorb or to capture CO2 will be in place. It's very important that if you want to be more familiar with this kind of net zero by 2050, you can go to the website of the International Energy Agency and you can receive more information. But now, this transition is extremely important. All the countries around the world at different speeds, but all of them have a common goal, and it's reaching net zero carbon emissions. And what is the important thing? The important thing here is that we are in a huge transition for the infrastructure inside the electrical power system, because we are going from a very centralized system that is characterized by huge power plants where we have a lot of synchronous generator. What I'm trying to tell you is that the old paradigm of the electricity industry was based on what we call the synchronous generator. And for that reason, that is the synchronous generator dominated system. But we are in this very important transition where we want to remove these thermal power plants that they are using fossil fuels or coal or any technology that is not environmentally friendly. And instead of those thermal power plants, we are installing more and more renewable energy, and also so many other new technologies. And what is important is that the future will look very different to the present or the modern power systems, because the massive penetration or deployment of photovoltaic power plants, they use a power electronic converter as interface to the classical AC grid. And also many of the modern variable speed wind turbines, they use power electronic converters as interface to the grid. And finally, new technologies like electric vehicles, and more important, these very important energy storage systems, they also use power electronic converters as the interface to the grid. With all of this, what I'm trying to tell you is that the future paradigm of the electricity sector, it will be based in a lot of renewable energy resources and many other technologies, but all of them have in common the use of power converters. For that reason, we are moving toward what we call a power converter dominated systems. And what you need to understand is that the electrical power system is changing in many directions. It's changing in the way that we are producing electricity. We are moving from very large centralized power plants with a lot of inertia, and we are moving for more environmentally friendly power generation that is small in size, highly distributed, and have low to zero rotational inertia. But also at the customer side, the way that we are using the electricity is changing. The customer is evolving from a passive element inside the network in only pay for receive electricity to a more active agent inside the electricity sector. In the future, the customer will be seriously participating in what we call the electricity sector, paying but also receiving compensation for producing electricity, because now the customer is changing and evolving to what we call the prosumer. It means that it's a customer that is able to produce electricity. And this kind of different behavior of the customer is creating that the distribution system will change. It will dynamically change the power flow directions, but also many other things. At the transmission level, well, the information is that now we will have the possibility of integrating relative large or utility scale energy storage system. And that is an advantage to compensate the issues related with variability coming from the primary energy resource of the renewable energies. Markets also, they are changing. The way that we used to have markets centralized with a national or a huge region inside the electrical power system and only considering energy markets, that is ending. Because now we are starting to consider the decentralized market for electricity, where the market is atomized, is reduced, is discrete in regional control. And finally, the operation, the way that we are operating the electrical power system is changing. And it must change to cope with all the new technologies that we are introducing. These new renewable energy resources, they are making the power system to behave faster and deeper and extreme and volatile. And for that reason, machine learning, real-time distributed control, and also artificial intelligence will be a very important part for the future operation of these converter-dominated power systems. But many people believe that this that I am talking about is something that will come in 100 years. And that is not true. I can tell you the way that we are migrating to reach the net zero depend of the country, the economy, and many other aspects. But we already have countries that they are facing the situation. One of my favorite cases is Australia. If you look, the National Electricity Market Operator, they published what they call the engineering framework in 2021. And in that engineering framework, they show this very important plot that I'm presenting here. This very important plot is presenting what we call the generation between synchronous generation and what we call inverter-based resources generation. It means wind power and solar power plants. I mean, here in the vertical axis, we have synchronous generation. Horizontal axis, we have inverter-based generation, essentially power electronic converter generation. And if you look those numbers, you can see that we are presenting in three different colors, 2018, 2019, and 2020. And what is important here to notice is the higher wind and solar penetration. Maximum levels increase on 28% in 2018, 47% in 2019, and what is very, very important is the year 2020, because in 2020, the total generation coming from wind power and solar power plants reached 52%. For that reason means that the synchronous generator was a minority. But what is extremely surprising is the forecasting created by the Australian market operator for the year 2025. If you look this plot over here, you can see the forecast that the operator has done in terms of the instantaneous penetration of wind and solar generation. And the market operator say that in 2019, and you can remember that it was under 50%. By 2025, two important scenarios, the scenario central ISP, they indicate that there are a lot of moments during the year where the instantaneous penetration of wind power and solar power plants will be 100%. With this important plot and the reference that I am locating here below, you can understand how important is the penetration of power electronic converters into the Australian power system. And similar situation is happening in many countries around the world, like the case of Great Britain or the case of the Texan local power system in the United States of America. What I'm telling you is that the power converters arrive to the electrical power system and they will stay here and they will increase the number. But what is the issue? And that is a very interesting and very important question. Well, the issue is that we are decreasing the number of synchronous generator installed in the electrical power system. The reason is that we are disconnecting many power plants, very old power plants, based on coal or fossil fuels, that they are decommissioning because they are pollutant or they are not environmentally friendly. But those very old power plants, all of them were based in synchronous generator. And now what we are doing is installing more and more solar and more wind power. Both of them, they have a lot of power electronic converters. For that reason, there is a decline on the synchronous generation and an increase on the penetration level of power electronic converters. But in this figure, I would like to summarize something that is extremely important that you understand. For many decades, we have been using synchronous machine in the electrical power system. Those beautiful machines, they are very simple in design, very robust, but the principles are extremely simple. And when we compare that with the new power electronic converters, they are totally different. It's like the two animals that I am presenting here, the horse and the zebra. Both of them, they have 4 legs, a tail, and 2 ears, and 2 eyes, a nose, and so on. But in reality, they are very different. And the situation is that we need to think the way that the electrical power system needs many things, many services, and how we can provide those services from the synchronous generators and from those amazing power converters. The reality is that the synchronous machine is not perfect, but for many decades or more than a century, those synchronous machine has been doing an amazing job, because a synchronous machine has the possibility of providing fault currents. During a short circuit, these machines are able to deliver a high current, and the machine is able to absorb a massive overload, because basically what we have at the stator is copper windings that they are using copper at the stator of the synchronous machine. For that reason, the synchronous machine is able to deliver additional fault current from the overload. That situation is not the same for the power converter, because without a massive overrate of the semiconductors, basically a power converter has no overload capabilities. But also, what is important is that the synchronous machine has a very amazing electromechanical property that is called the rotational inertia. And the rotational inertia is that allows the electrical power system to have a steady state frequency during the normal operation, and during a disturbance, this rotational inertia is able to try to recover the balance between generation and demand, limiting the rate of change of frequency, and that is extremely important. But also the synchronous machine is extremely simple, and we can add some control loops. And with those control loops, we can create what we call the frequency control. That's allowed that with this beautiful synchronous machine, we can keep the balance between the loads and the generators and the generation, and keeping the frequency under control. But this frequency control have different time scale, but the synchronous machine can do that in a proper way, in a simple fashion. On the other hand, another property that we didn't consider from the or didn't give so much attention and importance is the voltage control. During normal condition, we need to keep the voltages inside a quality band, and that requires that in normal condition, but also during faults, the machine must be able to provide reactive power to keep the voltage under control. And in that sense, the synchronous machine is able to assist with fault right through capabilities. And also, they have controllers that, like the automatic voltage regulator, to ensure the recovery after the disturbance. All of this is required to be implemented inside the power converter. All of these must be implemented using digital technologies, using digital signal processing measurements, and a lot of computational power inside the electrical power converter. And a property that we didn't take so much in account for many decades, and right now is extremely important, is the system strength. For many years, the synchronous generators, they have been providing what we call a strong and robust voltage signal. That means that the voltage has a sine wave form and also have a very defined or a very small bandwidth. But when we are using converters, the concept of system strength starts to be extremely important, because the power converter is very sensible about the system strength. If the voltage signal start to have different conditions not equal to the sine wave, or a massive change in the shape or the amplitude and frequency, well, it can happen the disconnection of the power converters, and that is what we need to understand. All those features that I'm talking about, fault current, system strength, voltage control, frequency control, rotational inertia, all of them were provided by the synchronous machine. And all of this was provided by the synchronous machine without any kind of complications or additional services. But right now, with the power converters, we start to rethink the way that we are operating the electrical system, because some of those services start to be crucial in order, or critical in order, to keep the power converters working. And that is the reason that right now we need to rethink the way that we are providing the services, who are providing those services, and also what is very important from the financial point of view is the compensation of those very important services. Well, what I will do very briefly is show you some of the impacts related with the reduced level of synchronous generators. As I said before, there is a tendency, and as we are declining the number of synchronous machines, the short circuit levels, they are starting to reduce. And what is very important is the impact of those short circuit level reduction. Many people believe that reducing the short circuit level is positive, what in reality is a very important complication, because the power quality start to be affected, because we start to have Thevenin equivalent impedance that they are higher, and they allow the propagation of the distortion of the sine wave. But also in protection is a very important problem, because the reduction of the short circuit currents start to negatively affect a very important protection scheme that we have been using for many decades. the overcurrent protection. The overcurrent protection require high overcurrents, high short circuit currents in order to identify the fault condition and also to locate the fault condition. Another thing is the voltage regulation. As we are declining the number of synchronous machines, well, there is a reduction on the reactive power support and the voltage support capability that we have. And now keeping in a steady state the voltages are creating a huge problem for the system operator. And finally, probably the most known of the issues related with the reduction of synchronous machines, and that is the reduction or the declining of the rotational inertia. As we are decommissioning many synchronous generator power plants, well, we are reducing the number of synchronous machines able to produce this important frequency response service that is called inertia response. And as a consequence, is keeping the frequency or this electromechanical property that keep the frequency inside the limits start to become a problem. And for that reason, well, we need to start to rethink the way that we are providing the frequency services. Here I will show you an example about the reduction of fault levels. Here you can see on the right hand side the voltages. You can see here the voltages during a pre-fault condition, and on the right hand side you can see the currents, okay? But in here, what we can see here is the short circuit currents. During a short circuit currents, of course, the terminal voltage start to decrease, but you can see here how the current is increasing from 3.7 kiloamps until almost 65 kiloamps. We are talking about huge, several times the rate current. And that is something that is able to be done by the synchronous machine. But if we talk about a power converter, now I am showing here on the top the voltage related to a synchronous machine, and below you can see the currents during a short circuit event. And what is very surprising for you here is that the short circuit current or the current during a short circuit is around 1 kiloamps. That is several times below the rate current that we were delivering by the PV system. And that start to create issues and problems related with the short circuits. And also, I tell you, this is a very important problem. This is a very important problem that has been already identified in the case of the GP system. It's already known that for 2035, many regions in the GB system will have reduction of the short circuit levels until more than 60% from the short circuit levels compared with 2015. And that is a big problem. Well, but I already told you about problems. And it's time to tell you about possible solutions. The future power converter dominate power system requires solutions, and us as electrical engineers must provide intelligent ways to solve these issues. And that is the reason that several authors worldwide they have been discussing mechanisms or solutions to enhance the system, the power system stability. And we recognize that there are two groups of solutions, what we call the short-term solutions. Short-term solutions, they are just basically creating the paths and gaining time in order to develop the proper long-term solution, the structural solution, and probably the final solution. Short-term solutions has been developed in many countries, as I say before, the case of Australia, the GB, the United States, the Texas system, they already has been working with grid connections. The grid codes has been modified and more requirements, more strong requirements has been asked for all those new power plants interconnected to the power system using power electronic converters. But this has been a short-term solution. Another short-term solution has been the creation of auxiliary services. There are few countries around the world that they have been developing very specialized services, some of them one-to-one contracts in order to provide the very specific service to solve very specific problems. For instance, the UK, the GB system has been one of the pioneers in providing auxiliary services for frequency, enhanced frequency response, and many other kind of frequency containment services has been developed in the United Kingdom. Also, in order to compensate the low short circuit levels and the lack of rotational inertia, synchronous condenser has appeared as a very important solution. Already, the GB system has signed one-to-one contract for the provision of inertia and short circuit levels. And some of those providers are basically synchronous condensers. Some other mitigation measures are related with monitoring and assessing the risk of the system. For instance, after the blackout in Australia, many system operators around the world start to look at the levels of rotational inertia. And one of the mitigation measures that has been implemented is monitoring the rotational inertia in the system, and if the levels of the rotational inertia start to be reduced, take control actions to improve that. However, all those short-term solutions, they are just short-term solutions to enable the long-term solutions. And two very famous long-term solutions are based on power electronic converters. Synthetic inertia has been a very interesting area for research for many years. I have been working on frequency control and stability for more than 10 years, and synthetic inertia was one of my favorite areas. But right now, in the last 4 or 5 years, many people start to think about grid forming control. To be honest, the grid forming control is nothing new, but it's something that we are starting to apply for electrical power systems, because the grid forming control has been for many years in the microgrid world. But now we are starting to use this kind of control technique for power converters, specifically voltage source converter, in order to enable the maximum penetration of renewables. Well, in the next few minutes, I will tell you about what I call the grid-friendly power converter. The grid-friendly power converter is basically the converter that is allowing integration of more and more renewables. And that is the job of this grid-friendly converter. To be honest, when we look into the control techniques that we can apply for the power converters, we have what we call the grid-following converter paradigm and the grid-forming converter. The grid-forming converter is what I call the grid-friendly, because it's basically trying to substitute the behavior of the synchronous machine. But what you need to understand is that they are not the same. The grid follower converter, the grid follower techniques is basically following the AC signal coming from the grid and attach to that AC signal. And to attach to that AC signal require a synchronization mechanism. There are many synchronization mechanisms published in the scientific literature. However, what we call the PLL is probably the most used and the most developed synchronization mechanism for grid followers. The grid follower is typically represented as a current source is controlled in a current source or a voltage source, but the typical grid following control is based in a AC controller, AC current controller. And for synchronization, we have the PLL. The grid forming control, on the other hand, is a very different paradigm. A very different paradigm where we don't need the synchronization with the AC grid, because the grid forming control is able to establish the synchronization with the grid in a very simple way, utilizing mechanisms similar to the synchronous machine. In the synchronous machine, the synchronization is based on the sine wave that is at the stator of the AC machine. And depending of that AC signal, the rotor position is able to deliver the active and reactive power. But in those conditions, we call that the grid forming. The grid forming has several advantages. One of them that is able to allow us reach 100% power electronic converters. But there are many things that we need to take into consideration. The power electronic converters using the grid forming control, there are many flavors. Many flavors, some of them are based in the model of the classical synchronous machine. What I am telling you is that they are grid forming controls that they are using what we call the virtual synchronous machine. And the virtual synchronous machine is basically a control technique that is mimicking the electromechanical behavior of the synchronous machine. There are some of those virtual synchronous machines that they follow even the flux leakages that you can find in the synchronous machine. And other control techniques, they are very simplified and they just use the basic second order differential equation, swing equation, to replicate the electromechanical behavior of the synchronous machine. But many other control techniques has been developed. The power synchronization control that doesn't require the PLL, where the synchronization is basically created by the shift of the current control, and the direct power control that is controlled by the voltage and phase, the voltage, internal voltage of the converter, and the phase angle. With all of this, what I want to tell you is that there are many flavors, there are many different techniques that you can find in terms of the grid forming control. And I highly suggest that you document about this. What is very interesting is that at this moment in 2022, we are in the pre-standard era. There are several countries, there are several transmission system operators that they start to include requirement for the grid forming converters. For instance, in the case of the GB, there is already a document that is presenting the requirements, the technical specification for virtual synchronous machine working in power converters working with the grid, with the virtual synchronous machine control technique. That is one of the grid forming techniques. However, we need to recognize that there is no a universal definition for this grid forming control. As a consequence, we are actively working in order to establish that very universal definition, or at least a standardized definition of the characteristic or services provided by this kind of control techniques. IEEE has a working group that is working on the development of a standard for the specification of this characteristic of grid forming converters. Well, but it's time to finalize this presentation. In this presentation, I have been discussing the important paths to reach the net zero carbon emissions. And a huge part of reaching that net zero carbon emission is on the shoulders of the power utilities. And changing the way that we are producing electricity, delivering electricity, and consuming electricity is a key element on this zero net carbon emission transition. And as I presented before, there are short-term solutions that many countries are already working on that, but also there is the long-term solution. What we call the grid forming converters techniques is basically one of the possible solutions for this. However, in this keynote, in this short presentation, what I want to bring to your mind is that probably we are doing things in not the optimal or the proper way. Why? Because we have been working in electrical power system for more than 100 years. The synchronous machine has been dominating the electrical power system for almost all the time. But the time has reached, the time has come that we need to rethink the way that we are designing and operating power systems. Because it's starting to be a minority. The synchronous machine start to be a minority. As I showed you in my statistics in the previous slides, the synchronous machine has been during moments minority inside the generation mix in Australia. For that reason, why do we need to keep thinking about inertia? Why do we need to keep thinking about keeping the frequency inside a very narrow margin that is only feasible and only useful for the synchronous machine? Why we keep trying to make a zebra look like a horse? Why we need to make the power converter look like a synchronous machine? When the reality is that we are the engineers that we are creating the future. Right now, we are creating the future. The future is now. We are creating the future now. And for that reason, we need to rethink the way that we are designing and operating the electrical power system to cope with this massive amount of power electronic converters. Well, this is the end of my presentation. I hope that you have many questions at this moment, and I hope that you are confused and you are angered to get more knowledge. It's time for question and answers, and that's all for today. Thank you very much for watching, and let's start question and answer. Thank you.